In this video, we're going to be summarizing curve sketching. Now, in pre-calculus, you should have learned how to sketch polynomials, rational, radical, exponential, logarithmic, and trigonometric functions. Using calculus, we can improve these sketches by finding the exact values of maximums, minimums, and inflection points. And we will be able to graph lots of functions we previously could not by studying their behavior. We will use functions characteristics, everything we learned in the last few sections, as well as other behaviors we will see here. So before we jump into an example, here is some important terminology. We have some asymptotes and holes, and then this next box gives us a basic guideline and steps to take to graph a function. So I will let you read over these, and let's go ahead and jump into an example. Example 1 says sketch a graph of h of x is equal to 5x cubed minus 3x to the 5th power using the guidelines on the previous page. Alright, for step 1, we want to find the domain of our given function, and this is a polynomial, and unless we restrict the domain of a polynomial is always going to have a domain of all real numbers. Okay, so moving on to step 2, we want to search for any x or y intercepts. So I'm going to start off by taking my function and setting it equal to 0. From here, I can factor out x cubed. And then I can use the zero product principle. So I'm going to set my first factor equal to 0, and my second factor equal to 0 as well. And for this equation, if I take the cubed root of both sides, we will get x equals 0. And then we get plus or minus the square root of 5/3. Okay, so from there we gain that our x-intercepts are 0, 0, and plus or minus the square root of 5/3, comma 0, and then our y-intercept is also located at the origin. Let's move on. So for step 3, we'd like to look for any vertical asymptotes or holes. Now, because our domain is all real numbers, there will be no vertical asymptotes or holes, and I know that this is a polynomial, so we're not going to have any of those. So I'll just identify that there are none. For step 4, we'd like to search for any horizontal asymptotes. And again, because this is a polynomial, we have none. Step 5, we'd like to look for critical numbers. So we need to find the derivative function. And once we found the derivative, we're going to set it equal to 0. Note here that I can factor out 15x squared, and then that will leave us with 1 minus x squared. So I can set both of these factors equal to 0 using the idea of the zero product principle. And I can also divide both sides by 15. So this equation will result in x equals 0. Here we'll get x squared equals 1. And then x is equal to plus or minus 1. Okay, so I've identified my critical values, and I'm using set builder notation here, or set notation. So these curly brackets, this is set notation, if you didn't know. And for step 6, we want to create a sign chart for f prime of x. Okay, so let's do that off to the side here. There is my number line, and my critical values, I'm going to place those at 0, 1, and -1. So I'm going to put little breaks here. And again, I just want to emphasize that this is my sign chart for f prime of x. And what you can do at this stage is you can plug in test values. So let's see, maybe I'll do -1/2, +1/2, -2, and +2. And what we're doing with these test numbers is we're plugging them into the first derivative and figuring out our sign chart, or whether it's positive or negative. So I rewrote our derivative function that we found earlier, and let's evaluate h prime of -2. And really, I don't care what the numerical value is. I only care about the sign, because we're doing a sign chart or a sign analysis. Okay, so this is going to become positive, and then let's see, -2 squared is 4, so that's going to be 1 minus 4, so that will be a negative number. So if I have a positive times a negative, that is going to come out to be negative. So here I will put negative, and I'm going to do something similar for the remaining test values. So I evaluated h prime of -1/2, and we can see that that's going to end up becoming a positive number. And I'll just quickly do the remaining two. All right, so I did the remaining intervals, and so this is what we found. And remember, when an interval has a first derivative that's negative, that means that the function is decreasing. And then when it's positive, that means that the function is increasing. And again, we have decreasing here. Now, let's kind of do some analysis. I know that at x equals -1, my function goes from decreasing to increasing, which means that at x equals -1, I'm going to find a local min. And then at x equals +1, I know that it goes from increasing to decreasing, and so at x equals 1, I am going to find a local max. Okay, so we are on to step 7, which wants us to create a sign chart for the second derivative. So let's go ahead and calculate h double prime of x. That's going to give us 30x minus 60x cubed. And eventually we're going to set this equal to 0. Let's go ahead and factor out 30x. That's going to leave me with 1 minus 2x squared, and then we're going to set this equal to 0, so I can set 30x equal to 0 and 1 minus 2x squared equal to 0. This is going to produce x equals 0, and then let's see, we have 2x squared is equal to 1, x squared is equal to 1/2, and then we get x is equal to plus or minus the square root of 1/2, which is equivalent to √2 over 2. All right, so now we're making a sign chart for the second derivative. I'm going to go place those values that we just found on my number lines. We have 0, we have positive square root of 2 over 2, and we have negative square root of 2 over 2. And essentially we're going to do the same thing where we make a sign chart using some test numbers. And square root of 2 over 2 is approximately 0.7, so I might choose some test numbers like 1/2 and 1, -1/2, and -1. So for the sake of time, I'm just going to go ahead and fill out those values. Here on this interval, the second derivative is positive, here it's negative, here it's positive, and then here it is negative. All right, so remember the second derivative tells us about concavity. So if I were to think about the concavity here, this is concave up, down, and down. So from here, we can move on to item number 8 on our list of guidelines or steps, and 8 asks us to locate inflection points. And as a reminder, an inflection point is an ordered pair where the concavity changes. So as we can see, there are inflection points at negative square root of 2 over 2, 0, and positive square root of 2 over 2. Okay, so item number 9 asks for y values of key points. So here's 9, and I'm just going to go ahead and kind of label these all as ordered pairs for ones that we haven't found yet. So I know that there is a local min when x is equal to -1, and to get the y value, we can evaluate h of -1 here. I'm just going to go ahead and tell you if you evaluate it, you end up getting -2. There's a local max at x equals 1, so the ordered pair is going to be 1, 2. And again, you can get that by plugging in x equals 1 into the original h function. And then I also went in and plugged in my x values for my points of inflection and plugged them into the original function to get these y values that I approximated here. And also I'm realizing that I forgot the one that's located at the origin, since these are my x values here. So I went ahead and I added that third point of inflection. And then the item number 10 asks for the end behavior, which, remember, end behavior is essentially just what's happening as the limit. You're taking the limit as x approaches infinity and negative infinity. So the limit as x approaches infinity of h of x. And let's see. This is a polynomial of degree 5, because that's the highest exponent. And then the leading coefficient, let's just remind ourselves, we had h of x was equal to 5x cubed minus 3x to the 5th power. Don't get confused, because remember, the leading coefficient is the one that's attached to the leading term, and the leading term is the one with the highest exponent. So our leading coefficient is -3. And so if this is a degree 5 polynomial with a negative leading coefficient, that means that my end behavior is going to be up, down. In other words, the limit as x approaches infinity of our function is negative infinity, and then the limit as x approaches negative infinity of our function is equal to positive infinity. So there is our end behavior. Finally, we are at step 11, which just wants us to sketch a graph of the function using all of this information that we just found. All right, so I just went ahead and I sketched the graph using technology. So this is something in terms of what our graph should look like. And let's identify some points that we already did. Here is our local max. We said that was at 1, 2. Here we have our local min. That was located at -1, -2. We know our x-intercepts. Those are happening here, here, and here. This x-intercept also happens to be a point of inflection. And then our other points of inflection are happening at about there and about here. And that is how we create this sketch of this functions graph. All right, let's move on to the next example. Example 2 says sketch a graph of g of x equals this rational function. So essentially we want to do everything that we did in the previous example, replicate all of those steps from our guidelines, and then sketch a graph. So step 1, we want to talk about the domain. And this is a rational function, so our domain is going to be all of the values we can plug in without worrying about dividing by 0. And because our denominator is x squared plus 1, x squared is the lowest it will be is 0 or some positive number. So the denominator is never going to equal 0, meaning that our domain is going to be all real numbers here. Then we have intercepts. So I'm going to go ahead and plug in g of 0. G of 0 is going to give me 0 plus 1 squared in the numerator, and then 1 plus 0 squared in the denominator, and that is going to equal 1. So that tells us that our y-intercept is 0, 1. And then to find any x-intercepts, I'm going to set the entire function equal to 0. Because this is a rational function, the entire function will equal 0 when the numerator is equal to 0. I can take the square root of both sides, and then solving for x gives me x equals -1. So I have that my x-intercept is -1, 0. For step 3, we want to identify any holes or vertical asymptotes, but since in this scenario our domain is all real numbers, we do not have any. Then for step 4, we want to find any horizontal asymptotes, and we're going to be able to find that by taking the limit as x approaches infinity of our function. So x plus 1 squared over x squared plus 1. If I were to expand out the numerator, this is equal to the limit as x approaches infinity of x squared plus 2x plus 1 over x squared plus 1. Notice that in the numerator and the denominator, we have both of those being quadratic functions, and so the rule is that we can take the ratio of the leading coefficients, which is going to be 1 here. So for this item, the horizontal asymptote is located at y equals 1. Now, moving on to step 5, we can find the first derivative so that we can find any critical values. All right, so I've gone ahead and I've used quotient rule to find our derivative, and then I've gone ahead and I've simplified it. Now again, our derivative is a rational function, so if I set this equal to 0, I really am just concerned with setting the numerator equal to 0. And that will give me 2x squared is equal to 2, x squared is equal to 1, and then taking the square root of both sides will give me x equals plus or minus 1. So our critical values are x equals plus or minus 1. And for step 6, we want to create a sign chart. So let me go ahead and make our number line. I'm going to place -1 and +1, and then we want some test numbers. So for some test numbers, why don't we use 0, -2, and +2. And here is our first derivative. So if I were to plug in, let's see, g prime of -2, notice that the denominator is always going to be positive since we're squaring it. So I'm just going to put positive down here. And then -2 squared is 4, -2 times 4 is -8, plus 2, that's going to be negative. So our overall answer is going to be negative here. Then we can evaluate g prime of 0. Again, my denominator is always going to be positive. If I replace x with 0, I'm going to end up with 2 in the numerator, and 2 divided by a positive number is going to be positive. And then finally, we have g prime of 2 is equal to, let's see, really I just care about the numerator because, again, the denominator is always going to be positive. If I plugged in 2, that's going to be a negative number. Okay, so I know that my function is decreasing, and then increasing, and then decreasing again, which tells me the conclusion is that at x equals -1, I have a local min, and at x equals +1, I have a local max. All right, so for step 7, we want to find a sign chart for the second derivative, and it's quite messy, so I'm going to leave it up to you to kind of work out the algebra using quotient rule. However, if you were to find the second derivative, I'm just going to tell you what it ends up equaling. All right, so here's what we get for our second derivative after it is simplified using quotient rule. Let's go ahead and now set this equal to 0. And remember, we just really care for a rational function when the numerator is equal to 0. So I have 4x to the 5th minus 8x cubed minus 12x is equal to 0. Notice that the greatest common factor of each of these terms looks like it's 4x. So that's going to leave me x to the fourth minus 2x squared minus 3 is equal to 0. And this is what I like to call a quadratic in disguise. It's a degree 4 polynomial that's left over. However, we could factor this quite nicely. So that's going to turn into 4x times x squared minus 3, and then x squared plus 1 is equal to 0. And we can set each of these things equal to 0 using the zero product principle. And this one will give me x equals 0. This has no solutions, or at least no real solutions. And then here we have x squared is equal to 3, and we get x equals plus or minus the square root of 3. All right, and I'm just going to tell you for the second derivative, this interval is negative, this one is positive, this one is negative, and this one is positive. Okay, so for 8, we want inflection points. And remember, this was f double prime of x. So inflection points are occurring where the concavity changes. So concavity, this is concave up. Oops, no it's not. That's concave down. This is concave up, down, and up. So concavity is changing at negative square root of 3. It's also changing at x equals 0 and x equals positive square root of 3. So for step 9, we want to find the y values of these important points, and I'm just going to go ahead and give these to you. So here are the ordered pairs, including the y values of some important points that we found. 10 is to identify the end behavior, and we already found that there was a horizontal asymptote. So horizontal asymptote at y equals 1. So let's go ahead and put all of this together now to sketch a graph. All right, so here's a sketch of our graph. I'm going to highlight some points. Here was our local max, which was located at 1, 2. Here's our local min, which was located at negative 1, 0. We have our y-intercept, which also... Oh, I think I have a typo. My point of inflection should have been at 0, 1, not 0, 0. So this is both our y-intercept, and it's also a point of inflection. So note there that the concavity is changing there. And then we have another point of inflection at square root of 3, 1.9. So that's about here. That's a point of inflection. And then we have another point of inflection that's about right there. And the last thing I wanted to highlight was that there was a horizontal asymptote at y equals 1. So if we continue to extend on the graph, our graph is going to get very, very close to y values of 1. And that's it for this graph here. Example 3 wants us to sketch a graph of the function f of x is equal to 3x minus 2 all over the square root of 2x squared plus 1. Let's run through our numbered checklist. So first on our list is we want to cover the domain. This is a rational function. We also have a radical in the denominator. So I need to make sure that the radicand is greater than or equal to 0, except it cannot equal 0 since it's in the denominator. So I need to make sure or consider the values of x. That will make 2x squared plus 1 greater than 0. Now, if you think about what kind of function this is, or think about the graph, here's the y-axis, here's the x-axis, and this is a parabola that has been shifted up 1 unit. It's an upward-facing parabola, and the vertex is at 0, 1. All of that is to say this thing is always greater than 0, so that's true for all values of x, which means that the domain for my function will be all real numbers. 2 on our list, we want to talk about intercepts. So I can take my function and set it equal to 0. And if I set my function equal to 0, I can just set my numerator equal to 0. And if I add 2 to both sides, I get 3x is equal to 2 and x is equal to 2/3. So this tells us that we have an x-intercept at the ordered pair 2/3, 0, and a y-intercept. That means that I just need to evaluate f of 0. And in my denominator, let's see, that's going to be just 1 in the denominator. And then in the numerator, I'm going to have -2. So my y-intercept is 0, -2. We want to consider if there are any vertical asymptotes or holes, and a vertical asymptote would be occurring when our denominator, so in this case, the square root of 2x squared plus 1 was equal to 0, and this is never equal to 0, so there are not going to be any vertical asymptotes, and the numerator and the denominator do not share any common linear factors, so there will be no holes either. So no holes or vertical asymptotes. Number 4 on our list talks about horizontal asymptotes. So we would like to take the limit as x approaches infinity of our function 3x minus 2 over the square root of 2x squared plus 1. One way we can start to go about this is in the denominator from our radicand, I'm going to factor out an x squared. And if I divide both terms by x squared, this is going to leave me with just 2. This will leave me with 1 over x squared. And if I factor out, or if I take the square root of that x squared, that's going to leave me with the absolute value of x. And then I can also factor out the x from the numerator. That will leave us with 3 minus 2 over x, like this. And we are dealing with the absolute value of x here, but because x is approaching infinity and will only be positive numbers, then we could just leave this as x, and what ends up happening is these x's will divide out. Now, as we consider x going off to infinity, this fraction here will go off to 0, and this will also go off to 0. So finally, our limit is 3 over the square root of 2, and if you wanted to rationalize this, it would be 3 root 2 over 2. Now, this is really interesting because if we were to do the same thing and take the limit as x approached negative infinity, we wouldn't get the same answer. So what would happen is at the step where we took the absolute value of x, so here, if we were considering x approaching negative infinity, then the absolute value of x would turn into negative x, and then our final answer would be the same, but just negative. So all of that is to say that we're going to end up with 2 different horizontal asymptotes, which is not super common, and so it's kind of cool to see that. So if I am talking about the horizontal asymptotes, there are 2. It's y equals 3 root 2 over 2 and y equals negative 3 root 2 over 2. So those are our 2 horizontal asymptotes. Let's move on to our next numbered item on our list. For number 5, we are asked to find critical values. This is going to require us to take the derivative of our function, and I'm going to rewrite f of x as 3x minus 2. I'd like to move the denominator up to the numerator, and we can do this by multiplying this by 2x squared plus 1 to the negative 1/2 power. And the reason that I'm doing this is so that I can get away with using product rule instead of quotient rule. So we have f prime of x is equal to the first function times the derivative of the second function. And I need to use power rule, so I will decrease the power by 1. And then we also need to multiply this by the derivative of the inner function, which is 4x, because I use power rule on this term, and then the derivative of 1 is 0, so we don't have anything there. And I think I'm missing a parenthesis. Well, actually, why don't I change this to a bracket? Okay, so now we have our plus, so we did first times the derivative of second plus the second times the derivative of the first function, which would be 3 in this case. Now let's do some simplification. I'm going to multiply this negative 1/2 right here with this 4x, and if we do that, we will get negative 2x. And so I'm going to put this in the front. And then I have the 3x minus 2. And then inside of my bracket, we have 2x squared plus 1 to the negative 3/2 plus, I'm just going to move the 3 to the front. Okay. Now, here's what I'm going to do next. I notice that I have a 2x squared plus 1 here and a 2x squared plus 1 here. However, they're being raised to different powers. This one's negative 3/2, this one's negative 1/2. I'm going to factor that out, and just like I would if I had something like star to the maybe negative 2 star to the 5th power plus 3 star squared. I factor out the power that's smaller. So if I factored out star squared, then this would be star cubed plus, oops, I forgot the negative 2. And then this would be 3 like that. So I'm going to do the same idea or apply the same principle here. I'm going to factor out 2x squared plus 1 to the smaller of the two powers, which would be negative 3/2. In the first term, that's going to leave us with just negative 2x times 3x minus 2. And then in the next term, that's going to leave us with 3 times 2x squared plus 1. And the new power would be negative 1/2 minus negative 3/2. That's negative 1/2 plus 3/2, which is 2/2, which is equal to 1. So I'm just going to put a 1 here, and this is what we have so far. Okay, let's go ahead and simplify the stuff in the brackets. If I distribute negative 2x, that's going to give me negative 6x squared. And then if I distribute to this term, that will be plus 4x. If I distribute the 3, notice that the exponent is 1, and so I can also just get rid of that, so that will allow me to distribute. So plus 6x squared, and then plus 3, and notice that these are like terms, so those will cancel out, and I will just simplify this down to 4x plus 3. And another way that we could write this if we wanted to was 4x plus 3 over 2x squared plus 1 to the positive 3/2 power since we moved it into the denominator. From here, we found that this was f prime of x here. So I'd like to set my derivative equal to 0 and also check to see where it might be undefined. The denominator cannot equal 0, so we're good there. And we just need to set our numerator equal to 0. If we solve this linear equation, we get that x is equal to -3/4. So I'd like to use the first derivative test. I'm going to make a table. All right, from here, I need to decide on some test numbers that fall in my intervals. Now, I always say that if 0 is a possibility, try and choose 0 just because it makes your calculations a lot easier. And then it looks like I would also be able to choose -1. It looks like I would also be able to choose -1 in this first interval here. And I'm just going to go ahead and tell you that I'll just go ahead and tell you that here this will be negative and this will be positive if we plug in our test values into our first derivative. And so this means that on the first interval we are decreasing. On our other interval we are increasing. We know that at x equals -3/4, our first derivative is equal to 0. And so if we go from decreasing to increasing, then we will have a local minimum at this value. Okay, so now we are, our sign chart, this was item number 6. Now we are on item number 7, which is to find or create a sign chart for our second derivative. So for our second derivative, I'm going to recommend that you use this form that's written right here, just so that you can use product rule on that in order to find our second derivative. I'm going to kind of skip ahead because it's a very similar process that we did to find the first derivative. And if you factor out the common factor, you get that f double prime of x is -2 times 2x squared plus 1 to the power of -5/2. And then that was factored out from inside our brackets, and inside our brackets we're left with 8x squared plus 9x minus 2. Now, from here, we would like to set this equal to 0 so that we can find potential locations of inflection points. And this goes in the denominator, or we could also just use the zero product principle. However, this thing will never equal 0, so we just have to set the thing inside the brackets equal to 0. And I would just recommend using the quadratic formula on this. If you use the quadratic formula and solve this equation, you will get that your two solutions are x equals -9 minus the square root of 145 over 16, and then the other solution is x equals -9 plus the square root of 145 over 16. And this is approximately equal to, if you throw that into your calculator, -1.3, and this is approximately equal to about 0.2, and this will help us make our sign chart. All right, so I know that plugging these values into my second derivative are going to give us 0. And then for the other ones, you can choose test numbers. In this interval, you can choose 0. This one, you can choose 1, and maybe -2 in that one. And I'll just tell you, this is negative, this is positive, and this is negative. So here we have concave down, and then this is concave up, and then this is concave down. And so we have 2 points of inflection. So point of inflection here and point of inflection here, since they change concavity. Item number 8, we kind of covered by this because we found a point of inflection at these two x values. For number 9, it wants us to find the y values of key points, and so we have a local min. We know that this is happening when x is equal to -3/4. I'm just going to go ahead and plug that into a calculator into the original function f of x, and the y value should be about -2.915. And then I have two different points of inflections that we kind of just found. One of them has an x coordinate of about -1.3, the y value -2.8, and then the other one 0.2, -1.4. And then for number 10, that talks about the end behavior. We already found the end behavior because we calculated the two different limit values as x approaches infinity and x approaches -infinity. So maybe I'll just copy down our horizontal asymptotes again. We have two. They are y equals plus or minus 3√2/2. Okay, so now we want to put all of this information together to produce a graph. All right, so here we have our graph. I'd like to just kind of highlight some points. Here we have our y-intercept. Here we have our local min. I know that we have a couple of inflection points. So this is one of our inflection points. So that's going to be about here-ish. And then another at 0.2, -1.4 would be about here-ish. We also have our two horizontal asymptotes. If you plug this into a calculator, this is about y equals plus or minus 2.12. So a little bit past 2, there would be a horizontal asymptote here. And you'll notice that as the graph extends, it'll get closer and closer to that. And then the other one is about here. And this one's interesting because note here that our graph does actually cross our horizontal asymptote, at least the lower one, around there somewhere. So that concludes this example. Example 4 says sketch a graph of the function m of x is equal to e to the power of 2/x. So let's start with our list. First, we'd like to find the domain. Now, this is an exponential function. Normally, we can plug in anything into an exponential function. However, our exponent here is 2/x. We cannot have division by 0. And so our domain ends up being all real numbers except for 0. And we can write this like this. And then for item number 2, we'd like to find any intercepts. I can't plug in 0, so there is no y-intercept. And if I were to set this function equal to 0, there's no power of e that will get us 0. So there are no intercepts. Our third item is we would like to find vertical asymptotes or holes. Now, this is a continuous function everywhere except at x equals 0. So the only place where there might be is when we approach 0. So let's see what happens. If I were to take the limit as x approaches 0 from the right-hand side of our function, let's see. If I plugged in really tiny numbers for x, that would lead to a really large number, since we're taking the reciprocal, a really large number in the exponent, which means that this goes off to infinity. However, if I were to approach 0 from the left-hand side of this function, then we would be plugging in really small negative numbers. So that means that I would have e to some really large negative number. I'm just going to give an example of that. Because it's negative, that would go into the denominator, and we'd have 1 over some really large number, which means that this is going off to be 0. Now, this is interesting that we have this scenario here. So this actually means that we have a vertical asymptote at x equals 0, and we have a hole. Let me put a hole at x equals 0. And it might not be immediately clear what that looks like, but we will see in just a moment, and I might even clarify here that the whole is at the ordered pair 0, 0. Okay, so number 4, we're going to take the limit as x approaches infinity of our function. And if our exponent gets really, really, really small, it's going off to 0. And so that would be e to the 0 power, which would equal 1. And this would work similarly if I took the limit as x approached negative infinity. So because they both approach 1, this means that there is a horizontal asymptote at y equals 1. All right, for number 5, we need to find our derivative. So m prime of x is equal to, I'm going to take the derivative, so that just leaves us with e to the power of 2 over x, and then I need to use chain rule by multiplying by the derivative of the exponent, and that's going to give us negative 2 x, and then I need to decrease the power by 1, so that's going to be negative 2. Okay. And I'm going to rewrite this. This is the same thing as negative 2 e to the 2 over x squared. And now that we have our first derivative, we would like to find any critical values. So critical values happen when the function's equal to 0 or undefined. Or excuse me, the first derivative is equal to 0 or undefined. So notice that we would get division by 0 if x is equal to 0. However, x equals 0 is not in our domain, so we don't have to worry about that. And just like we did before, similarly, this has no solutions. So if I tacked on a negative 2 in the front of this, that's not going to change whether that has any solutions or not, because I could just divide both sides by negative 2. So the implication there is that there are no critical values. If there are no critical values, then that means that we're thinking about our domain as just kind of one long interval of either increase or decrease. And so if I were to kind of split up my chart, even though 0 is not in our domain, well, maybe I'll think about it like this. So from 0 to infinity, these should have the same sign if I plug in a test number. So we could do negative 1 and positive 1 as test numbers into our derivative. Our denominator is always positive, and e to the power of 2x, regardless of what we plug in, is going to be positive. But then if I multiply by negative 2, these are going to be both negative. And so this means that f of x is decreasing everywhere. On the domain. Also, I'm realizing that our function was called m, so I guess this should be m prime of x and m of x. Okay, so moving on to item number 7, let's find m double prime of x. And I'm going to rewrite this as negative 2x to the negative 2 e to the 2 over x, so that I can use power rule on that. So if I think about this as the first function and then this as the second function, let's use product rule. So I have first times the derivative of the second plus the second times the derivative of the first I think I'm missing a negative sign here in the exponent. There we go. And now I notice that both of those have an e to the 2x. I'm going to factor that out. And that will leave me with, so I've kind of factored that out. It's in both terms. And if I multiply, let's see, if I multiply negative 2x to the negative 2 times this, that will give me 4x to the negative 4th. And then what's remaining after the plus sign would be this thing. So plus 4x to the negative 3. From here, I could do some further factoring outside of my brackets, and I can factor out a 4x to the negative 4. And then I would still have the e to the 2x, and then inside my brackets, I would have 1 plus x left over. Okay, that was a lot. So we have our formula for our second derivative, and I'd like to set my second derivative equal to 0 so that I can ultimately make a sign chart. We want to set our second derivative equal to 0, and we can use the zero product principle here. I'm going to go ahead and replace this and say this is equal to 0. And if I were to use the zero product principle, I would set each of these factors equal to 0. If I solved this equation, that would give me 0. This one has no solution. And then the last one would give me a solution of x equals negative 1. However, x equals 0 is not in our domain and no solution, so our only value that we are concerned with is x is equal to negative 1. So I'm going to go ahead and make a table for the second derivative test. So I have my table here, and we know that plugging in x equals negative 1 into our second derivative gives us 0. Then I can come up with some test values or test numbers. And if I plug these in, this gives me negative for the second derivative, and this gives me positive. This means that we have concave down on this first interval and concave up on this second interval. And so because the concavity changes, we have a point of inflection here. All right, let's move on to item number 9. There are no local extrema since we were not able to find any critical values with the first derivative. However, there is a point of inflection, and it's when the x value is equal to negative 1. And then that would make the y value e to the negative 2 power. And if we throw that into a calculator, that's approximately negative 1 comma 0.14. And then the end behavior, we know from previously that there's a horizontal asymptote at y equals positive 1. Let's put this all together now to create our graph. So our graph is going to look something like this, and let's do some highlighting of some things. I see here that x equals 0 is my vertical asymptote, but I also have a hole right here. And notice that there's no local extrema, and my function is always decreasing. So we said that earlier with our first derivative test, that m of x is decreasing everywhere on the domain. And we can see that here it's decreasing everywhere as we read from left to right. The y value is always going down. And then we also see the horizontal asymptote here of y equals 1. So that completes example 4. Example 5 says the graph of the first derivative f prime of x of a function of f is shown. Use it to answer the given questions. The capital letters represent x values. Part A says, on what intervals is f of x increasing? So some things that I'd like to highlight is this is the graph of the first derivative f prime of x. This is not the graph of f of x. However, part A is asking on what intervals is f of x increasing. So the way that we're going to go about answering this question is, remember that f of x is increasing when f prime of x is greater than 0. And so I'm going to draw my line here over my x-axis, And that's going to be happening when my graph is above the x-axis. So I'm going to kind of outline and highlight. It looks like that's happening between B and D, and then also happening here between F and I. So if I were to write this answer in interval notation, I would say that f of x is increasing on the interval from capital B to capital D, union capital F to capital I. Now, one thing that I would like to point out is you might ask yourself, look at this point, capital H, that lies on the x-axis, and that would imply that f prime of h is equal to 0. And since we have that it's positive before and positive after, and the f prime of h is equal to 0, that's going to mean that we're going to have a horizontal point of inflection there, and we're actually going to go over that answer again in one of the later parts. But what that's saying is I reach this point, and there's going to be a horizontal tangent line there, but it's also going to be a point of inflection. So it's increasing before and after that point, which is why it's included in this second interval here. All right, part B says, on what intervals is f of x decreasing? And this happens when f prime of x is less than 0. So we're going to be looking for all of the locations where our graph is beneath the x-axis. And so that's happening between A and B, and then again between D and F. Part C says f of x is concave up on which intervals? And remember, we have the concavity being concave up when f double prime of x is greater than 0. But we have the graph of f prime of x right now. So this is going to happen when the derivative of the graph we're looking at is positive. So if I take any point and I draw its tangent line, we know that it's concave up if the tangent line has a positive slope. So that's going to be happening everywhere between A and C. And I'm just going to highlight this now. So between A and C is when this graph is increasing. Also between E and G, and then between H and I. So all of these locations are where my first derivative is increasing, which will mean that the second derivative will be positive. In part D, we're looking for concave down, so that will be when this graph is decreasing. That's happening between C and E, as well as G to H. For part E, it says locate any relative extrema of f of x. So relative extrema occur when f prime of x is equal to 0. So on this graph, we're looking for x-intercepts, and that is occurring at B, D, F, and H. And we could have local maximums and local minimums. For local maximums, that is happening when our graph goes from increasing to decreasing. And so I'm looking for when before my critical value, it's positive and then negative. And that's happening at x equals D. And then a local minimum would occur when before that critical value, it's decreasing and then increasing. And so we have that that's happening at both B and F. Part F says locate any points of inflection of f of x, and that's going to occur when f double prime of x is equal to 0. And that means that on this graph, I need to find the locations where there are horizontal tangent lines. So that's happening at C, G, E, and H. And I'm going to write this in set notation instead of writing x equals for all of them. So I'm going to use this curly bracket, C, E, G, and H. Finally, in part G, it says what's happening at x equals h. And we alluded to this earlier. We know that there's a point of inflection there, but because the first derivative is positive both before and after, if I were drawing the graph of f of x, it would look something like this, where at h, it's concave down, but still increasing, since if I were to draw the tangent line, it has a negative slope. And then after that, it's concave up, but still increasing. And so that is a horizontal point of inflection. So there is a horizontal point of inflection at x equals h. That concludes this video. Thank you for watching.